So I was asked to, first of all, sir, thanks for the invitation. It looks like a great event. So thanks to the organizing for putting this together and also for inviting me to give a talk about how we can use physics informed neural networks in MRI, especially where we know that MRI can be expensive to acquire, so we typically are in a sparse regime of data. So I worked as the previous speaker, also in the heart mainly. Why we work on this topic is because cardiovascular diseases are one of the leading causes of death in the world, and the heart is actually a quite complicated system. It's multi-physics and it's also a multi-scale system. So here is a simulation that we have done. So this is a finite element model of a human heart, where you can see the electrical activity on top, how the electrical waves are propagating, and the bottom you can see how the heart is contracting. From left to right, we are increasing the amount of drag of a specific drag that we are applying, and you can see that just by changing the amount of drag, you can have drastically different responses um, to mechanical and also electrical responses. So this would be a case of fibrillation, and if you have this, you can die in a couple of minutes because there will be not enough blood supply to the rest of the body. So we would like to, given that the heart is so complex, we would like to personalize treatments, and we believe that computer models are a good way to integrate all the data that we have. But most of the time, and this is not only true for MRI, but for many clinical data, is typically very scarce and noisy. So now I would like to show you three different topics very briefly where we have used physics informed neural networks. So first will be in cardiac mechanics from MRI, then hemodynamics, also from phase contrast MRI, and I will also show some work that we have done in reconstruction. So the main tool that we will be using will be physics informed neural networks, which is a type of deep learning architecture where you not only train directly on data, like the segmentation and network that the previous speaker was showing, but we also have some physical knowledge about the system. So this is one of the early papers where they train a neural network to learn the velocity and pressure of this aneurysm just by looking at some concentration measurements. So here you can see this is the key difference, that now the network will also be trained here in this case by the Navier-Stokes equations, which are the ones that govern the physics of a fluid. So going to our specific application, our first goal will be to compute cardiac strain from multi-slide cine MR images. Cardiac strain is a very important metric because it tells us how the heart is functioning, and this is a metric that it goes beyond the typical and more simple approach of ejection fraction. That is something that you can get out of a segmentation, but here we would like to know how the tissue is actually deforming locally. So one way to do this is to use ultrasound, and this is very inexpensive, it's easy to access, but it lacks accuracy, and we typically only get a couple of views from ultrasound. And the other string will be to use an advanced MRI sequence like tagged MRI or dense. The problem is that this is very long to acquire, and it's also not clinically available in most sites. But here you can get more or less direct displacement information about the tissue, and then you can compute the cardiac strains. So we like to work with Cine MRI, which is the gold standard to assess cardiac function, but the problem is that it doesn't have any direct um, displacement information. And it's widely available. You can find tons of images of Cine MRI, even though in Chile they are not that common. And I guess that's the case for many developing countries. Um, So how do we do this? So this is a different approach. So here we train one neural network, a very small neural network per case, per patient. So it's not a case of supervised learning in the sense that we need a lot of annotated data. We'll be just solving for one a specific patient. So here we have a network that takes an input, a coordinate in the heart, and also takes a time of the cardiac cycle, and it outputs the displacement field. Um, so and then once yeah. Here we will be deform a template image with this deformation field, and then we will compare it in this case to a reference image, which is just by clinical practice set at end diastolic phase, so when the heart has its biggest volume. And well, I mean, this is a standard image registration problem, but what we add here is that we know that the cardiac tissue is nearly incompressible, and we also embed this property when training the neural network. So this is how our loss function looks like. So first we have an image similarity, which is standard for any image registration problem. We have a near incompressible hyperelastic regularization, and that's a very fancy term to say that we would like to keep the heart, that the cardiac tissue should maintain its volume locally. And then we also have some background regularization. So this is how our regularizer looks like, but the key term is that here we have J, which measures the volume changes. So if it's bigger than 1, it will be an expansion, and if it's lower than 1, it will be a compression, and here we try to keep it around 1. So this is how our results look like. So one of the challenges in Cine MR is that typically you get maybe 10 cuts or 8 cuts along the longitudinal axis of the heart. So here you can see that the resolution here is pretty bad. I mean, the slide thickness will be around 8 millimeters. But if we look at the other plane, the resolution is much higher. So it's challenging to specifically capture how the heart is moving up and down with these images. But you can see that we can track the images quite well. So we tried this for 15 different subjects, and you can see here that in most of the cases we can preserve the incompressibility of the tissue. Here the range is quite small, and in most cases it looks sort of gray, which is what we should expect. And this is showing in systole where the deformation is maximum. So if we compare to other methods, because we use this in a public benchmark, and we can actually achieve state-of-the-art, the errors are smaller than the other methods. Just to put this in context, all these are traditional registration methods, and this is a convolutional neural network trained in a supervised, I would say semi-supervised way, and you can see that the performance is not that great. So now if we take a closer look, uh, so here these points represent manually tracked landmarks, and we would like to have that the red dots are on top of the green dots. You can see that with our methodology we can do that quite well, but as I told you before, we have some issues capturing the longitudinal displacement. And here, for example, with the convolutional neural network, you can see that it basically predicts zero longitudinal displacement, which is the part that is harder to capture. So now the goal was to compute cardiac strain, and we can do that. I mean, cardiac strain are related to the derivatives of the displacement field. So if we here we can get pretty good results in the mid region of the ventricles. So we have a negative longitudinal strain, a negative circumferential strain, and a positive radial strain with values that are here. Typically the hardest part is to capture this high radial strain, and we can get higher values than the other two methods. But if we look at the basal and apical regions, these are actually pretty hard to capture. The main reason for that is that, for example, the basal plane here tends to disappear when the heart is contracting because it's moving down, and another structure will appear like the valves, and that it really confuses the algorithm. And in the apex region, we don't have too much information, and also sometimes the apex disappears from the images. So that was the first application that I wanted to show. And the second application is related to cardiovascular hemodynamics. And here we would like to estimate some hemodynamic parameters from phase contrast MR images. So this is our model. So this is the aorta. So here is here the aorta is connected to the left ventricle, and this is the descending aorta, and we have some more branches. So here, as I said before, the blood we will assume is governed by the Navier-Stokes equations, which is these are the forms. We have some boundary conditions, meaning that the blood cannot pass through the vessel wall. We also have some inlet here that represents the blood that is coming from the heart. And also for boundary conditions, we will have a special kind, which is called Bin-Kessel, which acts like it's similar to an electrical circuit with resistors and capacitors, and it's meant to model how the downstream vessels will behave. So this will be our forward model, and what we can actually measure to tune all these parameters will be some planes of phase contrast MRI, where we can measure directly the velocities of the fluid of the blood moving. So in this case, we will just use 3 different cuts. So again, we have a very similar setup. So here we will have a neural network that is trained just for this case, where it will depend on space and time, and it will predict. Here we will not predict directly the velocities. We will predict a potential such that if we take the curve, we will get the velocities, and the reason for that is that we can get rid of one of the equations of the Navier-Stokes, and it will always be satisfied because in this case the mass will always be conserved by the neural network. For the outlets, we actually need another neural network which represents the evolution of these Bin-Kessel elements. That they will have some parameters, which are represented here. So these are some proximal distal resistances, some proximal resistances, and some capacitance. And we would actually like to infer from the data these parameters. So, and the data that we have will be these measurements that I showed, and also a mean pressure curve, because we need some sort of reference, and this could be just the cuff pressure that you can measure non-invasively. So here are the results. So you can see this will be our ground truth simulation. We did this with finite elements. Um, and then this will be the trained physics informed neural networks. And then we actually apply some post-processing to clean the solution with finite elements. And this is that result that is a bit cleaner than the pure pin solution. So taking a closer look here, what we do for the post-process solution is that we take the learned parameters, the learned inlet, and parameters from pins, and then we plug it into a finite element solver, and then we recover the solution. So you can see that in diastole and systole, the results are actually quite well for the three different methods. Um, but here the velocities are quite high and the flow is sort of uniform. But you can see here, for example, some artifacts in the physics informed neural networks where you can see that the blood is coming out of the wall because the boundary conditions are only imposed as a soft constraint. So that's why that's the things that we can correct with the finite element simulation here. And now if we take a look at the end diastole, the flow is actually quite complex, but the velocities are much lower, so they are 1/10 of these ones. Um, and we can recover some structures here, not so much but with the pins, but with the post processing we can recover the main um, the main characteristics of the solution. And I wanted to also show some another topic, which is MRI reconstruction, specifically applied to cardiac cine. And our goal here is to accelerate the acquisition of cine MRI, of cardiac cine MRI. Um, and this is not so much related to physics informed neural networks, but we use sort of the same idea of training a single network per case. Um, and if we call the MRI physics or the forward operator of MRI the physics, we can also call them physics informed neural networks, I guess. So one of the key challenges in cardiac imaging is that the heart is always moving. So a couple of strategies to address this that are used in clinical practices. First is breath holding to avoid the respiratory motion, then ECG gating to synchronize the acquisition of the images, and also another idea is to use motion robust trajectories like radial sampling. Um, so we would like to have the patient the less time as possible in the scanner. So um, to do that, we can do undersampling, where basically we acquire less lines in the case space. And here you can see an example of different trajectories with different acquisition times. So this is 30 milliseconds, this is 78 milliseconds, and you can see that the images are improving, but in the Cartesian case they are actually never that good, and for spirals and radial they are quite okay. So how do we solve this problem? How can we try to get good images from undersampled data? Is that here typically, classically, what we do is that we have a set of all the possible images. So we represent an image with pixels, and then we try to minimize the data that we have by the difference between the data that we have and the image, and then we apply the forward operator. So typically it's involved the coil sensitivities, the Fourier transform, and then some undersampling pattern. But this problem is severely opposed, so we need to apply some explicit regularization to get a reasonable image. So what we are trying to do here is to reconstruct these highly undersampled images, but we'll use a technique that is called implicit neural representation, and the idea is very similar to physics-informed neural networks. So here we will represent the image with a neural network. So we, instead of optimizing the pixels, we will actually optimize the parameters of a neural network. So in this case, we will have an implicit regularization. So we will have no explicit regularization term, but we will play with the architecture of the network to get have networks that if we train them on data, they will produce reasonable images. So this is a little bit the idea of implicit neural representations. So we have the same architecture that I showed you before. In this case, we are trying to learn a color image. So one of the key points is that if you just use a regular neural network with just ReLU activations, you will get an image that looks something like this. So we need to do something to avoid this. But if you use Fourier features, which is a coordinate embedding, where we just transform the input coordinates by some cosines and sines, and we give the neural network some higher frequencies, we can learn this image much better. So in our case, we need to do learning. Scene images are dynamic images, so we also need to encode the time. So in this case, we created a new embedding for time and space, which we call STIF, and it basically has the regular Fourier features plus some periodic features that are because we know that the cardiac cycle is periodic, so we also embed that knowledge. And this will be the dynamic part, and this will be the static part. And here also the images are complex, so we need to have two outputs. One will be the real part, and one will be the imaginary part. So to perform the reconstruction, we actually not going into all the details, but one of the key parts is that we are working with radial trajectories, and we use a trick with the Fourier slice theorem that allow us to convert this problem into a tomography problem with the random transform. So that makes the training a lot easier, and we avoid using the non-uniform FFT. So we tested this in a number of cases. There's a public data set with real trajectories that we played with, and this is the reference, and this is our proposed method with 26x undersampling, and you can see that it worked quite well. But to be fair, a classical method like RASP also works fairly okay, but we think our images are a bit sharper. So we have also done is just instead of doing the typical cine where you during one breath hold we acquire repeated spokes in the gate space across multiple cardiac cycles. We have also done just with one cardiac cycle. So this will be real-time imaging, and we can do quite well in this case as well. So just to conclude, we can use physics-informed neural networks to solve our large range of inverse problems with sparse data, especially coming from MRI in cardiovascular biophysics. And what we like to do is to learn more from the images by embedding or learning also from the physics, so we can get more advanced metrics like cardiac strain or hemodynamical parameters. And also I have shown how we can reconstruct our images at very high acceleration factors. So now what we would like to do is to go from end to end, so work with the image reconstruction and also the quantification, all in a single pipeline, because now we first reconstruct and then apply the subsequent algorithms, but we believe that there could be some synergies if we put them together. So these are the references, and thanks for your attention.